invite you all to Peter's thesis defense. Every student at MIT I found is unusual in some way. Peter is unusual in unusual ways. To me, just the way he thinks about things. I mean, he was a half physics undergrad and a computer science undergraduate. So I've learned a lot from just kind of how he thinks about problems and how he thinks about kind of the world, the technical world. And in our group meetings, one of the most interesting things is how Peter has an opinion on everything, and many of those opinions are very well informed, even when it's something that's unrelated to anything he's thought about or worked on. So it's been great having Peter in our group and working with him. There's been some challenges for me because there's a lot that I didn't know about how he thinks about things. But I also want to especially call out Peter. We started a course on mobile and sensor computing, and Peter was the first TA for that class, and he was absolutely terrific in helping us build the labs, build the assignments. We still use those labs. We just make incremental changes to them over time. And then he has this lecture on GPS, and when he graduates, one of the most daunting tasks for me or whoever lectures that is to cover that. So we recorded his lecture, so I just have to understand now all of the details. So anyway, he has worked on a number of different problems and will tell us about spatiotemporal variations and some of the problems that he's worked on today. So the defense works, we do the public part of the defense, and then you can ask some questions. We hope to end that in an hour, and then there's a private portion of the defense of the committee. And I want to thank Muriel and Jerry for being on this committee. So take it away. Oh, I also should say, want to thank Peter's parents for making the trip from California. Enjoy.
Thank you, Maya. Thank you very much. I'm all warm and fuzzy. It's true. I'm thrilled that you could all make it here today. I'm going to be speaking about two of my projects that touch on a very challenging aspect of wireless systems. This challenge arises because wireless signals have a fundamental tendency to vary in time and space. We can predict that the signals will vary, but we cannot in general predict how they will vary. Here's a quick illustration of variations in time. I'm going to play back a visual recording of a signal. I want you to follow the stripe between the blue arrows. And please, because of the configuration of this room, please let me know if I'm standing in front of something that you need to be able to see.
I'd be able to help you.
Oh, that would be much appreciated. Thank you, I'm honored. So, let's suppose that this is the signal that we're trying to pick up. We've tuned our radio to that channel. Time runs from top to bottom, and darker colors represent stronger signals, while lighter colors represent intervals of time when the signal faded away. Watch how the darkness of the line varies. Oh, I can hear you now. Oh, no, I lost you. I can hear you now. Can you hear me? Hello? No, you faded out there. Lost the call. When the strength of a wireless signal varies in time, this is usually an indication that something physical is moving. Either the sender of the signal, the receiver of the signal, or some physical object in the space in between. It could even be tree leaves swaying in the wind, although there's no leaves on the trees right now. We can try and get a similar grasp of the variation of wireless signals over space with this lovely illustration. This was created by a British physicist who wanted to know where he should put his Wi-Fi router. If the router is placed at the black circle, and if Dr. Cole's assumptions about how well concrete absorbs microwaves are just so, then the bright spots on the map show where he should sit to get the best signal. But scoot a few centimeters to the left and lost it. When the strength of the wireless signal varies with space, this is usually an indication that signals are following more than one path. Wireless signals are waves, which means that when they're following more than one path, the waves following different paths may add or subtract, depending on the distances involved. If they subtract, there may be little or no signal left for the receiver to pick up. In wireless communications, the goal is to faithfully deliver information between devices. Signal variation with time can interfere with that goal. The first project I will present today is a protocol that assists wireless communications systems in adapting to temporal variations. The key takeaway will be the remarkable effectiveness of this abstraction that we call the decoding CDF. In wireless localization, the goal is to establish an accurate relationship between signals and places. Signal variation with space can interfere with that goal. The second project I will present today explores the question of when localization systems designed to tolerate spatial variations can and cannot be fooled by a determined adversary. The key takeaway will be that the way to hide a signal or to unhide a signal is to be the one with the largest number of antennas spread over the largest space. I'm a ham radio operator, and you can trust me when I say that I need more space for my antennas. It's a scientific fact. Let's focus now on the first of these two projects. Okay, suppose that someone, Alice, wants to use the internet from her wireless phone. When she opens her browser, her phone assembles a small chunk of data that represents a request for her favorite web page. The phone then prepares to emit a wireless signal bearing this chunk of data. In the past, Alice's phone would have sent out the data in a single one-way burst. But Alice has a brand new 4G phone. This new device does not send the data out in a single burst. Instead, it relies on a back and forth negotiation that divides each chunk of data across several bursts. Every time the device finishes a burst, it asks the other side, have you got it yet? Have you got it yet? If the answer is no, then the device has to send another burst. The reason for this is that today, the vast majority of wireless devices cannot send and receive at the same time. Even when Alice is on a call, her phone is never sending and receiving at the same instant. Instead, it rapidly switches back and forth between the two many times per second to keep up the illusion that the call is two-way. There are some costs to that approach. Every switch takes time, and that time adds up. RateMore is our system for controlling these costs. The RateMore algorithm calculates the costs and benefits of different strategies for using wireless signals on devices that cannot talk and listen at the same time. The algorithm uses these costs and benefits to determine exactly how long each burst should be, so that Alice's phone will waste as little time as possible waiting for feedback. In particular, RateMore is designed to make this determination in concert with a data protection scheme called a rateless code. The rateless code represents a way to protect data from radio interference or noise by introducing redundancy into the message. As much redundancy as we need. RateMore takes as input a simple model of the wireless physical layer. This model, which we call a decoding CDF, abstracts away the details of the rateless code. It also represents everything we need to know about the strength of the signal. The RateMore algorithm then calculates the costs and benefits of different strategies for sending and listening. Using the decoding CDF, RateMore computes the best possible rule or schedule for how much redundancy should be sent over the channel and when the sender should pause to listen for a feedback signal. I'd like to start by showing an example of what I mean by scheduling feedback. This will allow me to demonstrate what a transmission schedule is and why this problem is important for building faster wireless systems. After that, I'll show you a picture of what RateMore is doing with this information in order to produce, a transmission schedule. There's a WYSI graphics and all, but the key takeaway is that this input, this decoding CDF, has a surprising amount of power for summarizing the physical layer. It's the right abstraction. both because it gives us everything we need, and because it is succinct, directly observable, and universally applicable to rateless codes on the wireless channels that we are studying. I will spend some time elaborating on that idea in a little while. To motivate this idea of a transmission schedule, let's briefly consider the simplest wireless system with reliable delivery. After the system sends some data, it listens for feedback from the receiver. It can repeat the payload if needed. The payload includes check information so that the receiver can tell if it's been corrupted. We observe that retransmissions are slow. So systems like Wi-Fi use forward error correction. This reduces the number of retransmissions, but it also increases the best case transmission time, which poses a limit on both throughput of the system and on the number of devices that can be on the network at the same time. By introducing more cycles of feedback, we can reduce the amount of redundancy that needs to be sent under good conditions. The system shown here holds some redundancy back until it receives a negative feedback. Under good signal conditions, the system follows the short path, transmitting for less time, and under poor signal conditions, it follows, so here's the short path. Under poor signal conditions, it follows the long path, transmitting for a longer time. Note that under poor conditions, the scheme requires at least 2 feedback cycles for each packet.
So down is an error and out is I didn't hear you.
Yes, sir.
Okay, got it. Time out.
A feedback cycle requires the sender to stop and wait. The length of this pause may be anywhere from 64 microseconds for Wi-Fi to 2 milliseconds for 4G LTE. That's a very long time when bits are measured in nanoseconds. So the cost of feedback may be quite high. The value of feedback is for knowing just the right amount of redundancy to send. This idea of breaking up the redundancy into smaller pieces and executing more than one feedback cycle is not limited to only 2 cycles. If we take this idea to the extreme, we have a feedback cycle for every single piece of redundancy. This is what is called a rateless code. Wait a minute. Didn't we just say that feedback is costly? And now we're talking about these fancy codes, these rateless codes, and they require a lot of feedback? Well, you don't have to get feedback after every single symbol. What the rateless code does is it makes it so that you could if you wanted to. So the question is, when do we want feedback? When do the benefits outweigh the costs? RateMore identifies the best possible transmission schedule to take advantage of feedback, weighing both the costs and the benefits. So let's squash together the parts of this diagram. We don't need the arrows, we don't need the start bubble. All we really need is the length of each blue rectangle. And we'll keep the purple diamonds around to represent pauses for feedback. This is what we're calling a transmission schedule. It gives the number of units of time spent sending redundancy before each pause for feedback. We call these units of time symbols. In this case, the transmission schedule is 5 symbols before the first pause and 5 more before the second pause. When we reach a pause, we ask the receiver for feedback. If it says yes or ACK, we go back to the beginning of the schedule and we start again with fresh redundancy, bring us some new redundancy from a new chunk of data. If the receiver says no or NAC, then we proceed to the right to the next burst in the transmission schedule, and we consult the schedule to see how much more redundancy to send right now. The objective of RateMore is to maximize throughput, time averaged throughput. We accomplish this by making the average time spent on each chunk of data as small as possible. If we send very few symbols in a burst, it's not likely that the receiver will have made much progress towards decoding at the time of the next pause for feedback. In that case, the next feedback will probably be negative, and we will end up sending yet another burst. The rule is, don't ask a question if you already know the answer. On the other hand, when the receiver does finally decode the message, we will find out right away, because a pause for feedback is never very far away. So if this decoding succeeds somewhere in the middle of a burst, we don't have to wait very long to reach the end of the burst and find out that we were successful. Compare this to the case where the sender sends more symbols between pauses. Now it can be more certain that decoding will succeed. The feedback's more likely to be positive, which is good for us because it means we can move on to the next chunk of data. But on the other hand, because pauses for feedback are now fewer and farther between, the sender is likely to overshoot the mark quite a bit, sending too much redundancy and wasting time.
Peter?
Yes, sir.
Just clarification. The reason that you don't try sending something in that region there is because you're assuming it's a half duplex.
Yes, sir, that's exactly right. So, how does Ratemore know which transmission schedule is the best one? We use a strategy of induction. This requires a bit of a mental leap. I'm going to break up the scheduling problem into smaller problems, and I'm going to ask you to suppose, just for a minute, that we've already solved some of the subproblems. I'll draw the ones we've solved in blue, and the ones we haven't yet solved in gray. Now I have to share two things with you. First, how do we solve one of the gray problems using what we know about the blue problems? And second, how do we get started? Where does the first blue problem come from? Let's run through a quick example of how to solve one of the gray problems. We're going to represent our work in progress transmission schedule as an array of pointers. Each blue box will get an arrow that says, suppose I'm here in box 8. I've already sent 8 symbols worth of redundancy. The solution for the subproblem was, let me see, aha! I should send 6 more symbols before pausing for feedback. And if I was in box 14, I should, having sent 14 symbols already, I should send, say, 12 more before pausing. All the blue boxes get arrows representing the solutions that we have so far. So, how about box 7? Okay, what does Ratemore say that we should do if we've sent 7 symbols, and the receiver says that that's not enough? Where should the arrow starting from box 7 go? Well, it has to go to one of the blue boxes because you can't unsend symbols, so you can't go to the left. So every blue box is a potential target. First, Ratemore will compute the time required to send that many symbols. Next, it will add in the time which would be needed to get to a successful decoding if the next feedback turned out to be negative. It will apply a discount to these costs according to how unlikely each situation is to arise. This is where the decoding CDF comes in. Ratemore can evaluate it to determine the probabilities of getting negative feedback. Now we look for the minimum and identify that as the best choice, and we fill in the box for arrow 7. Ratemore then moves on and completes the rest of the calculation in the same way. The transmission schedule can now be read off by following the arrows starting at 0. Send 7 symbols, then send 4 more, then send 4 more, and so forth. Now, I told you that we had to start with blue boxes in order to make more blue boxes. So where does the first box come from? We can't work backwards unless we have some place to start. Turns out that for certain special decoding CDFs, certain special inputs to Ratemore, the best strategies eventually settle into a steady state. Beyond a certain point for these special inputs, all the costs and benefits for one box are exactly the same as those of the next box and the next one after that. In fact, all of these many subproblems running off to the right are really just one easy subproblem in disguise. Turtle in disguise. What have I heard that before? Okay, what if we don't have one of these special inputs? How does this help? It turns out that by slightly tweaking the decoding CDF, we can make it special. This means the problem will settle into a steady state, and all the subproblems beyond a certain point collapse into one. The best part is, the solution of this modified problem is actually quite close to the best solution of the original problem. Any loss of throughput, remember how we're trying to maximize throughput? The loss of throughput can be made as small as we like. Okay, I've shown you a picture of what RateMore is doing, and I've highlighted the role of the decoding CDF in allowing RateMore to compute how likely it is to receive negative feedback at each point. As I said earlier, the key idea I'd like for you to take away from this part of the talk is that the decoding CDF has a surprising amount of power for summarizing the physical layer. When we need to discount the costs in RateMore according to how likely certain outcomes might be, the decoding CDF tells us what we want to know. What is a decoding CDF? It is a function that takes as input a certain number of symbols and produces as output the probability that a particular decoder in these particular conditions will decode successfully. Yes, sir?
In the feedback, when you get a knack, do you also, does the receiver also tell you how many symbols it's received?
We are assuming that in the forward channel, the metadata, that is the structure that says, I'm going to send you this many symbols, is unambiguous. In the written form, not in my presentation, I give some details on how some of that information can actually be implicit, and the receiver can know how many symbols it should be expected to receive. Does that answer your question?
I was wondering, does the sender, when it receives a knack and it knows that I asked if the receiver has received everything and it says no, do I now know how many symbols the receiver has actually received?
Yes, you assume that the receiver has received all the symbols you sent. They might have been, each symbol might have individually suffered some disruption from the noise, but the symbols all got there.
Mm-hmm.
This is an additive noise channel.
Okay, this is the noise channel. Okay.
Yes. Thank you. Okay. This decoding CDF is an empirical quantity. We can draw it on a graph with input symbols along the horizontal axis and output probabilities on the vertical axis. I told you that the decoding CDF abstracts away the details of the rateless code. RateMore doesn't need to know how the code is structured or how the decoder works. These things can be treated as black boxes. All RateMore needs to know is how likely decoding is to succeed. The curve shown here is a schematic of the real thing. After some minimum number of symbols, below which decoding is not possible, the CDF rises gradually towards 1. What if signal conditions are better? The message should be easier to decode, so most of the time we shouldn't need as much redundancy. Sure enough, when the signal-to-noise ratio is higher, the decoding CDF moves to the left and becomes sharper. What determines this CDF? Depending on the specific rateless code, you will get a different curve. Depending on the condition of the wireless channel at a particular moment, you may get a different curve. Even depending on the details of the decoder, you may get a different curve. For instance, if Alice's phone needs to save battery life, it can scale back the amount of effort that it puts into decoding any given incoming message. This is, in particular, a valid thing to do with spinal codes. I'm less familiar with whether you can do this for other codes, but under some conditions it is possible. With the phone not trying as hard to decode, more redundancy might be required on average, giving a different decoding CDF. The point of the decoding CDF is not, I can tell you one curve and be done with it. The point is that the decoding CDF serves as an abstraction barrier, a point of decoupling between the rateless physical layer and the rateless link layer.
As the physical layer slowly varies, does the decoding CDF vary this curve?
Yes.
Okay, so it's saying they're measuring the signal-noise ratio dynamically with some over the last period or interval.
Exactly.
Mm-hmm.
We could use standard techniques for measuring the signal-to-noise ratio, and then we could look up in a table how well we expect the current code to perform under those conditions. The problem is that when you send an LTE signal to a phone with an Intel chipset or a Qualcomm chipset, the exact same signal will be decoded with different probabilities. So not only do we need to know about the instantaneous state of the channel, but we also need to know how strong this receiver is in some sense. There could be other factors that affect this. Ultimately, we only care about that information in aggregate, and we don't need to estimate all of those individual parameters. Does that answer your question, sir?
Thank you.
Yes,
How, if at all, does the number of bits of information that you're trying to convey affect the CDF?
it's an excellent question. The typical behavior for good codes, that is codes which approach the Shannon capacity of whatever channel they're designed for, is that this will become a very sharp curve as the number of bits that you're transmitting in a single encoded message goes towards infinity. Now, spinal codes are kind of squishy. By that I mean the transition region for spinal codes between not decoding at all and decoding perfectly is much wider than it is for certain other codes. Nevertheless, they seem to do very well within this rateless model. So whereas a traditional fixed rate code, a fire and forget code, needs a very sharp threshold behavior to transition from not decoding to decoding so that it will approach the capacity, that's not a requirement for rateless codes. And part of the question that we were trying to answer with this work is, given that we have these codes which now work, but only if you get feedback every single symbol, how much of that benefit carries over to the real world where you don't get feedback every single symbol? Does that answer your question? Thank you very much. The decoding CDF is sufficient. It tells RateNor everything it wants to know to schedule transmissions under a given cost of feedback. The decoding CDF is succinct. It consists of a few thousand numbers at most. The decoding CDF is directly observable. Every time decoding succeeds, RateNor learns how many symbols were required for decoding. This number is a sample from the decoding distribution, and it carries information about how the CDF is evolving. The decoding CDF is robust. We've had remarkable success in approximating it with a 2-parameter Gaussian family, with minimal loss of throughput. Most of all, the decoding CDF works for any rateless code on the additive Weigand Gaussian noise channel. I want to add something here. Is this all absolutely optimal? Is this strategy the best that can possibly be done? No, it's not. In particular, if you break through the abstraction barrier of this decoding CDF and you go rooting around in the details of the rateless code, it's conceivable that you may find that some data messages are protected better than others. So, photographs of cats sent from Alice's phone could conceivably turn out to require less redundancy than photos of dogs having the same size and bytes. If so, the sender would like to know about it. That would mean that the sender, who knows exactly what message is being sent, has an opportunity to fine-tune how much redundancy it will use. If you have that opportunity, it wouldn't be optimal to ignore it. The decoding CDF is an average over all possible messages, cats and dogs. Does this work well in practice? Yes, it does. Here's a real, honest-to-goodness set of decoding CDFs for a particular rateless code. These are for spinal codes with 256-bit packets. These are quite short packets. The statement that things get sharper as you go to long packets doesn't really take hold in this regime. Each curve represents a different set of channel conditions. Conditions are best on the far left and worst on the far right. For this code in particular, the transition from no decoding to full decoding for the can be quite gradual. At the lowest signal-to-noise ratio curve, there's more than a factor of 2 between the number of symbols where decoding begins and the number where it becomes a sure bet. If I zoom in on the far left, I'll start to be able to see more detail in the behavior of this code under the most favorable channel conditions. these little plateaus represent situations where additional symbols give very little incremental benefit. And the sharp walls between the plateaus represent situations where incremental symbols give great benefit. Given these curves, Ratemore will automatically take full advantage of this plateau structure in rateless codes, even though Ratemore doesn't know what it is about spinal codes, in this case, that created these plateaus in the first place. Ratemore can do this thanks to the sufficiency of the decoding CDF. I mentioned that we've had
So that was done by, that's a simulation that you,
Yes, sir.
okay, you got the data out of the simulation.
Yes, sir.
Okay.
This was thanks to joint work with Jonathan Perry. He
Got it.
conducted extensive simulations over a large parameter space, and he was able to extract this data from his data
Good.
set.
Okay.
Thank you. Okay. I mentioned that we've had remarkable success in approximating the decoding CDF with a two-parameter family, with minimal loss of throughput. Here's what that might look like in practice. We've simulated a slowly varying channel represented by the dashed line. Time runs from left to right, and higher is better. For a given rateless code and a given size chunk of data, it is not possible to reach the dashed line. The best that any link layer protocol can possibly do is shown by the red line. To reach the red line, a link layer protocol has to be given the ground truth decoding CDFs and the signal to noise ratio.
What, when you say channel capacity, is this for that particular modulation? What modulation are you using?
I believe that this is the Shannon capacity for the AWGN channel, so it's just log of 1 plus SNR.
Okay, so, and you're using what modulation in your system?
That is abstracted away in the data set that I'm using. What happens is the spinal code will perform search over the space of messages rather than over the search of constellation points.
I guess what I'm saying is it could be that you're actually doing better because you're constraining your modulation by your transceiver, so your upper bound is lower than that. Your capacity for that given modulation is lower.
It could be. I'm not certain I understand your question.
Your capacity, you have a AWGN channel, so your
Yes.
capacity would assume a Gaussian continuous
Mhm.
input or some approximation thereof.
Mhm.
Your modulation is generally something else,
Mhm.
qualm, 16 qualm, whatever the heck,
Mhm.
and therefore you might actually be doing better.
Okay. That's
Right,
a good
because
question.
given that you only have that modulation, you cannot get to.
That's an excellent question. One of the first questions, actually one of the things that got me into Hari's group in the first place, is I was standing in Hari's office during visit weekend 9 years ago, and we were talking about spinal codes, and I asked him if he had considered using a Gaussian output constellation for the encoder. And he said, yes, we have considered that. It doesn't seem to make a big difference in practice. Now, you can do the analysis, and you can find the finite gap between the capacity under a finite-sized quantum constellation and the capacity under the Gaussian distribution. The gap to capacity due to that effect is small compared to the gap you're seeing here.
No.
Please correct me.
You're going to have a different dashed line
Yes,
representing different modulation schemes.
yes. What I'm saying is the supremum over all possible modulation schemes is shown by the dashed line.
Correct.
And I'm further claiming that the distance between the dashed line and the red line is not mostly due to modulation, it's mostly due to other things.
That's possible. I was just wondering, because there is a big difference.
You're absolutely right.
Okay. I mean, it speaks well. You could actually be you could actually be closer to some, platonic optimum, basically based on whatever your constellation is.
Yes, I could draw a tighter bound if I chose the constellation, but in this case, the constellation is part of the code, not part of the simulation that I'm doing here.
No, I was just wondering, that's fine.
Thank you. Okay. for a given rateless code, okay, we have this red line represents the ground, okay, the red line represents scheduling pauses for feedback under the assumption that the scheduler knows the actual true decoding CDF and it knows the SNR. We just give it these things and we ask it how much time is needed to decode. But rate more, our system, using no knowledge of the instantaneous decoding distribution and no knowledge of the instantaneous SNR, but instead doing online learning of this 2-parameter decoding distribution, is able to reach within 2% of this ideal adaptation bound. And this is the basis of our claim.
What's alpha?
Alpha is the the inverse time constant of an exponentially weighted moving average for the parameters of the distribution.
Gotcha.
So in particular, this blue curve that I'm talking about, it only pays attention to the last 10 or so packets when it makes its decision about what the current decoding CDF looks like. Whereas the green curve and the teal curve lag more significantly because, they're unable to as quickly adapt to the current channel conditions because they have a much more conservative learning parameter. They're averaging over a much longer time. So, thanks to RateMore, Alice, remember Alice? Alice can use her phone efficiently, saving time and power, and freeing up network resources for other users. RateMore determines when a rateless sender should stop to ask for feedback. It takes advantage of feedback without incurring her huge costs because it takes the costs into account in the optimization. RateMore can do this because the decoding CDF tells it how likely it is to receive negative feedback under any possible strategy. The decoding CDF is sufficient, succinct, observable, and robust, and code agnostic. Estimating it online is feasible and works surprisingly well even during fading. Next, I'm going to move on to the second of my 2 projects for today. Society faces significant stresses concerning anonymous behavior on the internet. On one hand, anonymity may protect dissidents and whistleblowers from reprisal. On the other hand, it may also shield criminals and predators from justice. As public policy evolves, technical standards will face pressure to follow, and wireless standards are no exception. Current Wi-Fi technology makes no effort to perform surveillance, but it also makes little effort to prevent it. There's a quote I like to share from journalist Russell Brandom. Brandom was talking about the problem of wireless anonymity when he wrote, "In theory, a person with the right equipment can always trace the bark back to the dog." Is that true? Is it necessarily the case that using a wireless network makes an individual identifiable? In our work, we have explored a number of measures, countermeasures, and countermeasures for tracking moving sources of wireless signals using physical layer information. Our idea was to cook up the most powerful de-anonymizer that we could think of, and then to characterize its strengths and weaknesses. The key takeaway from this project is that tracking is almost always possible if the tracker has more antennas than the device being tracked. And inversely, tracking is almost always impossible if the device being tracked has more antennas than the tracker. It turns out, though, that access to more physical space is also a critical factor. If the device being tracked is physically very compact, then its many antennas cannot behave independently, and the effective number of antennas is lesser, allowing tracking. Let's put a face on this problem. I'd like to introduce you to Betsy. Betsy poses this question to Alice. Dangerous people are looking for me. If I use my laptop to connect to a wireless network, am I putting myself and my family in danger? We will call Betsy the sender, and her adversary the listener. Betsy wishes to push traffic through the network, and her adversary wants to passively eavesdrop on all wireless signals, tie each signal back to a particular sender, and ultimately to learn the identities of the senders. The key question is, when can two transmissions be tied back to the same device? That is, can I tell from any given pair of transmissions whether they have the same sender? We call such a procedure a same sender test. This may not be the obvious question to ask. What I ultimately care about is whether I can participate in the wireless network without leaking my identity. How can I claim that the key to wireless anonymity is the non-existence of a same sender test? If a listener can tie two transmissions together, and then it can tie those to a third, and so on, it can build up a chain of transmissions, all tied back to the same sender. If the listener then finds a way to de-anonymize any of these transmissions, it de-anonymizes all of them. This chain is as strong as its weakest link, and leaks are common. Suppose the sender and listener are connected to a secure Wi-Fi network with WPA2 Enterprise. As of a year ago, that was the best option. I haven't had the opportunity yet to learn about WPA3, but we're all very excited. Because of the way such a system works today, the listener can decrypt some of the sender's messages. In particular, they can decrypt broadcast and multicast transmissions, including ARP, Windows file sharing, multicast DNS, and Dropbox file synchronization, leaking a great deal of information useful for de-anonymizing the sender. It's not enough to patch every application and secure every protocol if the listener can de-anonymize a chain of transmissions. Eventually, the pattern of behavior revealed by this chain of transmissions will uniquely identify the sender. So, to achieve anonymity, the sender will have to stop the listener from building such a chain in the first place. That is, the sender's goal is to defeat every possible same sender test. Today, Wi-Fi makes the listener's job easy. Besides MAC addresses, in 2016, at the ACM Conference on Wireless Security, CSAIL et al. Built a same sender test using packet timings. Others have shown that imperfections in radio hardware generate unique radiometric signatures for each sender. In each case, the technical issues seem tractable. It's more of a cost problem. MAC address randomization techniques have been proposed and deployed. There are network protocols like Vuvuzela by Van den Hoef et al. That are resistant to traffic analysis. As for radiometric signatures, modern radios are flexible enough to correct for almost any imaginable non-ideality in software with enough effort. However, there are other ways to associate packets that depend only on the nature of radio waves, on the way that they spread out and interact with the environment. So, how would the strongest imaginable attacker exploit these physical layer properties? The radio information is contained in an object called the Channel State Information, or CSI. The goal is to use this CSI for fingerprinting signals. Our first contribution is a strategy for the listener. The listener wants to tell whether two transmissions are from the same sender, and it does this by extracting a hash of the sender's identity from the channel state information using our fingerprinting procedure, which we call REST. Our second contribution is a strategy for the sender. The idea is to dynamically change the shape of the sender's antenna without having any moving parts. Each configuration is used for a single transmission. By reprogramming an array of switches, the sender can access an exponentially large number of antenna shapes, all occupying the same physical volume. This allows a sender with a small number of antennas to hide from a listener running REST with a larger number of antennas, which would not be possible otherwise. Our third contribution is a theoretical bound on how many antennas the sender can emulate in this way. What we found is that a large smartphone can access at most a few dozen distinct antenna patterns on the 2.4 gigahertz band. With greater numbers, the antennas become indistinguishable to the listener, which is the same as saying they can be tracked. I'm going to speak briefly about the first of these three puzzle pieces, and I'd be happy to take questions afterwards about the others. To see how REST works, we need to understand what determines the channel state information measured by the listener. Here's the thought I want you to keep in mind. If a listener can extract from the CSI variables that the sender cannot control and are unique to that sender, then the CSI can be used to build a same-sender test and anonymity is in trouble. The Wi-Fi signal undergoes a series of distortions on the path from the sender to the receiver. Channel state information summarizes those distortions. Most distortions, the ones we care about, are multiplicative, meaning that doubling the input signal doubles the output. We pack all the multiplicative distortions together and we call that the CSI. We can think of the signal as flowing through this block diagram from the top left to the bottom right. Before I go into detail, I'd like to show you what this looks like as an equation because it's really very, very, very simple. The ideal signal, x, gets multiplied by a matrix H, which represents the channel state information. So when you see H from now on, I mean channel state information. Unless it's in the middle of the word the. The signal measured by the listener, y, is just the product, H times x, plus noise. Now, we can show what each step does. Remember, each step represents a multiplicative effect, and they all combine to form H, the channel state information. The transmission starts inside the sender as an ideal, undistorted Wi-Fi signal. The sender chooses the matrix, the pre-coding matrix, to map the ideal signal onto its finite set of antennas. This matrix can be anything the sender wants, but it's usually chosen so that the signal is strongest at the intended receiver. Now the listener is not the intended receiver, so the strength of the signals won't be maximized or anything in particular by this matrix. The output of pre-coding is one signal for each antenna at the sender. Next, the sender antennas cause their own non-idealities, and the signal that emerges from each antenna as radio waves begins to spread out into the environment. The environment is full of obstacles that absorb, reflect, or distort the radio signal. There might be a number of distinct paths that the signal bounces along between any given sender antenna and any given listener antenna. The multiplicative effect of the environment is a sum over these paths. The reason for the pre-coding matrix is it gives the sender some amount of control over this process. If the sum over these paths would otherwise be 0, pre-coding can make it add up to something non-zero instead. That's good for the intended listener because 0 doesn't carry any data. We're going to abstract away this complexity of the sum over paths. We can think of the effect of the paths of 3 stages. First, a radio wave is produced at the sender's location. Next, it interacts with the environment. Finally, it's measured at the receiver's location. Now, the listener cannot simply break the CSI down into separate parts corresponding to each of these contributions. The parts are irreversibly combined together in the final measured quantity. Notice, however, that many of these factors are not under the sender's control, like the environment, the listener's location, and the listener's antennas. The sender's antennas are some bulky solid-state circuitry that takes up part of the space inside the phone. And without the technique that I mentioned of switching the antennas around, generally the sender's antennas cannot be altered. Remember, the listener is looking for variables that the sender cannot control and are unique to the sender. The sender's location is just such a variable. So, now we can repose our question. Can the listener decompose the channel state information to get the sender's location? Actually, this question is too specific. The danger to anonymity is not just if the listener can learn the sender's location, but also if the sender can learn a proxy, any other proxy, for the sender's identity. So, can the listener extract a hash of the sender's identity from the channel state information? The answer is yes, provided that the listener has more antennas than the sender. This is exactly what REST does. It takes the channel state information as input and separates out the part that corresponds to the sender's pre-coding from the part that depends on the sender's antennas and location. The decomposition of this variable into separate pieces is not perfect. REST throws away some of the information about the sender's location. What we show is that the stuff that it discards is precisely the things that the sender can corrupt by changing the precoding matrix. REST returns all the information about the sender's identity that the sender cannot control, and none of the information that it can control. In that sense, REST is the correct generalization of the so-called angle of arrival techniques to this adversarial setting where the sender does not want to be localized. Any angle of arrival system that relies on more variables than the ones REST uses can be fooled, and any angle of arrival system that relies on fewer variables than the ones REST returns can be improved. I told you that this channel state information is a matrix, a square full of variables. We can visualize this by drawing an arrow to represent each column of this table. For instance, here's the channel state information matrix for a 2-antenna sender, as observed by a 3-antenna listener. So here's some set of received signals that lie in plane in which these arrows lie. When the sender varies the precoding in an attempt to confuse the listener, the vectors shown in blue and red move, but the plane that they lie in does not. This plane is what REST uses to characterize the transmission. This intuition generalizes to other numbers of antennas, other than 2 and 3. But let's continue with that example. The plane represents exactly the parameters the sender can't control that characterize the sender. So what REST needs to do is extract a representation of the plane formed by the columns of this matrix H. How do we represent a plane? There's a very nice way of doing this using a function which we call P. When P acts on any vector, it, on or off the plane, it returns the nearest vector that is on the plane. We can get P from H with just a little bit of algebra, and we can compare these functions P to determine whether they correspond to similar planes. And the comparison is very simple. It just comes down to taking the square root of a sum of squares. Up to this point, I've glossed over the problem of how the listener gets the CSI in the first place. In practice, this measurement is only an estimate, and so both H and the fingerprints we compute from it will be noisy. So what do we do in this case? Well, if we have an understanding of how the noise could have perturbed our estimate, we could consider every possible realization of this random variable. For each possibility, there would be one corresponding value of H, because in order to explain a given estimate under a given possibility for the noise, there's only one possible underlying truth. What we do then is we compute this fingerprint for all of these possibilities and average them together. This gives us a more robust estimate of the fingerprint P. What is remarkable is that we can accomplish this without doing an infinite amount of work. In fact, our final approximation is quite simple, and it's exact for strong signals. Our 2017 publication contains additional details, and in particular, a result from fundamental physics that shows how packing more antennas into a compact device must lead to diminishing returns. The key idea...
I missed the words. Must lead to...
Diminishing returns.
Diminishing returns. Thank you.
Thank you. The key idea is, if you want to be sure you can hide, or if you want to be sure you can catch someone who's hiding, you need to have more antennas than they do. And the more antennas you want to have, the more space they must take up. You cannot simply interdigitate a large number of antennas and expect to always be good at hiding or tracking. Thank you.
Now, if you have, because we're talking about a few gigahertz signals,
Yes,
we're talking about a few centimeters wavelengths.
Mhm.
As a consequence, small motion of the transmitter makes big differences if there's a highly reflecting environment, which is complicated reflections.
Absolutely.
So does that give the sender more ability to hide by just wandering around in little circles?
That is
for
an
example?
excellent question. Yes, it does, provided that the sender can keep its mouth shut while it's moving.
Got it.
If the sender continues to chatter while it is in the process of moving,
Of course, I see
then the
that.
tracker can follow the trail of breadcrumbs
Right.
and establish a link between the chain before
But-
and the chain
But
after.
has any one packet then walking some other place, any other packet, and so on, is equivalent to having lots of antennas, especially in a highly reflective environment.
Exactly. Zach, you were next.
Yes, when you say more antennas over more space, essentially you assume the antennas have some minimum spacing between each other. Not that you maintain the same number of antennas, but expand the space that they cover.
What we establish is, in the limit where you pack an infinite number of antennas into a small box, the effective number of antennas is finite. Does that answer your question?
Yeah.
Thank you.
It's pretty cool that you're packing a lot of number of antennas and using one chain, still one transmit or receive chain. I was thinking if the antenna behavior changes, if you're able to activate different substrates below the antenna so that you change the coupling between them, how much more degrees of freedom might this actually give you in additional security? Because, and you need to know the code, of course, at the receiver.
That's a good question. What I can tell you is, Venkat has been doing some work on switchable antenna arrays to explore a very similar idea. But ultimately, it doesn't matter whether your antennas are driven with one front end or many front ends, whether they have ground planes or no ground planes. Our result has to do with is a statement about distributions of current within the volume of the phone. If there's a ground plane, there will be induced currents on the ground plane, and all of the effects that you're familiar with ground planes having reduces to a new distribution of currents.
But if the substrate, if you're changing the substrate that are below it, then you're changing the distribution of the current altogether, and that randomizes the channel.
Yes, we randomize over that as well. I would be happy to talk with you more about it afterwards. Is there anyone else? Okay. It has been my pleasure to share with you today some of the fruits of my collaboration with these amazing individuals. I am deeply grateful to all of you. My committee has further helped me to tie all of my work together in a cohesive whole. Professor Medat has graciously offered me her expertise in communication optimization. Without her guidance, a number of the results in my dissertation that I'm most pleased with would never have been possible. Professor Sussman has been a mentor to me for 11 years. He's provided me with many uplifting conversations and many warm cups of tea. I particularly appreciate the uniquely crisp and computational revisionist approach to linear algebra and calculus that Professor Sussman has shared with me. He also made me a special gift of a round to it for those of you who know me. I'm very pleased that my parents were able to join us today. They've gone above and beyond in so many ways that I am lost for words. Thank you. In addition to serving on my committee and working closely with me on some of my projects, Hari has provided me with patient and reliable support through his tireless work to keep the lights on around here. I understand that SoftBank has offered to keep the lights on at Hari's startup company for a very long time. My deepest thanks to Hari and my congratulations. Professor Emer has offered a thoughtful and listening ear to me for many years. I'm thankful to him for our many encouraging conversations and for encouraging me in my minor studies in quantum physics. Some of the work I presented today would not have been possible without those studies, so I suppose you could say that I majored in the minors. Sheila Marion has been tireless in making financial arrangements for my research and in making sure that our conference travel was well supported by the Institute. My thanks to her. My thanks also go out to all of my colleagues and friends for their wisdom and encouragement. Thank you for keeping me going. At this point, I'd like to open the floor for questions. Well, I see that I answered all of your questions successfully, so, thank you.
Peter, I really like the CDF graphs for the number of symbols in spinal codes. If I understood it correctly, you have a different CDF for a different SNR,
Mhm.
low SNR, high SNR.
Yes.
And the cool thing about this is that this approach is not only useful for wireless, but it also is useful for, say, optics.
Hmm.
Because anywhere that you're measuring SNR, you can come up with the number of symbols that are optimal depending on the SNR.
In fact, you could even do this for wired comms.
Yes, optics where the signal is going over a fiber optics
Mhm.
cable. The thing that I'm wondering though is that you had another graph that several colors, each representing a different SNR CDF, or spinal cord CDF,
Let me
right?
see if I can bring you that.
Yeah. What was the distance between the SNR?
Okay, that one is right about.
It's right after the,
You know, he's finding it.
Here we go.
yeah,
Mhm.
or the
Uh,
one maybe before it.
do you want this
let me
one?
see.
Actually, the one after is lower, you expand the low end.
Yeah.
Is this the one you had in mind?
That's the one.
So what is the distance in terms of SNR between these CDFs?
These are separated about 1 decibel in SNR.
Okay, so good. So
And I run
how
from, I
stable
think,
is your SNR? Am I constantly moving between these CDFs?
that's an excellent question. One of the ways of posing radio is to say, here is a bag full of CDFs, run your off-the-shelf signal-to-noise ratio estimator, and use the CDF that corresponds to the closest SNR or interpolate between them or something. That's one way of doing it. The advantage of that approach is that you know how close to optimal you are in a certain sense.
So at one point I make a measurement, I decide on the CDF.
Yes.
In another interval I make another measurement.
That
How
would be
off
the
would
way.
I be? Do you have a sense of...
That's not what we're actually proposing.
That if you did that,
Okay.
you would be subject to the whims of this off-the-shelf SNR estimator,
Mm-hmm.
which in theory they work perfectly and in practice they're terrible.
Yeah, okay.
When I interned at MediaTek, we talked about just how unreliable these things can be.
Yeah, okay.
So our alternative, which sidesteps the problem entirely, is to learn the CDF directly rather than learning the SNR and then picking the CDF that matches that SNR. Does that
Yeah.
address your question?
So you're not jumping around.
Right.
Okay.
So this is related to my previous question. What's a symbol here?
A symbol is a single complex number sent out over the AWGN chain.
With what sort of resolution again? What's your modulation?
For this example, I believe it's 2 to the 20 quam.
2 to the 20 quam?
Like I said, the receiver is doing a search over messages, not a search over constellation points.
But that's not your constellation point. You don't have a 2 to the 20 quam. It's not an actual 2 to the 20 quam. It's you're looking at a vector and interpreting that as a 2 to the 20
I
symbol.
think if I may step in, I think there's sort of this general many wireless systems. You kind of construct the, you take some bits and then you map it to. one of the
Right. That's what I'm
frequencies.
asking. So it's not
Yeah.
a 2 to the 20
No,
quam.
right.
It's you're looking at a string over. So your actual transceiver.
No,
Anyway,
I'm serious.
we can
It
talk later.
really is.
Yeah, it's the approach here is not to pre-construct the constellation and map the bits to different symbols, but instead to take the bits and map it directly to a complex number.
Yeah.
So now, in theory, it's an infinite resolution, but in practice, it's digital. Therefore, there's some,
Yeah, and that's what.
and that translates into effectively 2 to the 20 quam because it's sort of 10 bits per symbol in 2 dimensions.
Yeah.
So that's sort of the way in which this line of work has been done, is to sort of not have 2 separate layers where you have bits to symbols and the symbols are predefined, but instead to say let's directly construct a complex number to send out. Does that make sense?
Yeah, we can talk about it
Yeah.
in the closed session.
Okay, thank you. Any other victims? Alex,
Do
thank
you
you for
have
coming.
any estimates for how much additional throughput or power savings we get over current transmission schedules in use?
That's a great question. I'm gonna have to switch out of my PowerPoint to get you the answer. Let's see if I have it open. Google will help us. So let's go to rate more Iannucci Novicon 2012. Oh, not connected to the internet.
Good.
You can wait more.
They can't track me now!
That's the other request.
Let's, oh, wait a minute. I actually have the right page open in my thesis. So, so the question you asked, Alex, if I understand you correctly, is how much does this actually help? So we define a couple of metrics. The answer is it can be subtle. The best case scenario is about a 20% improvement in throughput. But that's, for an example, very small packets. So the quantity that shows the most dramatic improvement is if you add up the amount of time spent waiting for feedback and you compare that with the absolute minimum that you could possibly get away with under any scheme. The amount of feedback that would be absolutely required just to determine whether the receiver has gotten the message. Okay? We call the excess of time spent soliciting feedback beyond that minimum overhead. And we're able to reduce overhead by more than 5 times.
Any other questions? All right, thank you, Peter.